The linear growth problem, I assume went fine, I hope.
Yeah.
But the exponential growth, not so much because I think you need the review, but because it leads into today's, like I said, right? So an exponential growth, the amount grows by the same factor each time, or the rate proportional to how many there are at any moment. So in calculus, you'd say dA dt, or the rate of change in the amount over time, is constant times amount. Now, why is that? You told me it is, and that's what it is.
You have spoken.
That is not good enough for yourself. So think about in compound interest.
The change of A in time is in respect to itself and a constant.
Okay, so if I told you your account grew at 4%, would that mean that in year one you could tell me how much it grew by?
No.
Yes.
Could you tell me how much it grew in year one?
Yes.
You could have. All right, how much did it grow by?
4 times.
Okay, how much money did it grow by? Okay, so to answer the question, you would have to know how much was in the account. Yeah, because it's going to grow by 4%, but 4% of what, right? So that's what this is talking about. The rate at which it grows is proportional to how much is in the account. It matters how much there is. Think bunny population. If I said, all right, the population doubles every 3 years. So how much will it double in 3 years? Or how many bunnies will it grow by in 3 years? You don't know. You don't know how many bunnies are doubling. Do you agree? It would be proportional to how many there were. We need to know the amount of bunnies. All right? Now then, if we start in that differential equation and work backwards towards the amount equation, then what do we do first? Separate the variables. Do you agree K could go on either side, but it's logical to leave it over there. So let's go dA over A is K dt. It's crucial that you show that. Now to solve a differential equation, that means integrate to get the original equation. So if I integrate, it's the natural log of the absolute value of A equals KT plus a constant. Yay? All right. Now, the initial condition, let's say at time 0, the amount equals the initial amount is put in. Then for A, I would get the natural log of A naught, or the initial amount, equals 0 plus C. And therefore, C is the log of the initial amount. Yay? All right. Now, if I throw that in for C and keep going, the natural log of A is KT plus natural log of absolute value of A naught. Yay?
Yeah.
Right, now we're going to solve for A. What do I do next?
Subtract from the natural log.
No, what else? Exponentiate. So absolute value of A equals. When I exponentiate, can I exponentiate here, exponentiate there, exponentiate everywhere? Or do I have to exponentiate the whole side?
Whole side.
Whole side. It must be done to the whole side, like square root, okay, or square. So it's e to the kt plus natural log of A naught. Yeah? How do you get rid of the absolute value? Plus or minus. And let's also clean up the right side a little. What is anything to, anything to a sum of exponents? How else could it be written? Yeah, it's multiplication, yeah? So that means this is the same as plus or minus e to the kt times e to the natural log of A naught. Let's write the e to the kt on the back end. And what is plus or minus log of A naught? Plus or minus absolute value of A naught. Typically, if you're dealing with living things, we don't sweat all the absolute value in the plus or minus. Typically, it's small. Okay, are you with me? Cool. AP Bio people. So, if I put bunnies into that field, will the population grow exponentially? Forever?
No.
Why not? Field's too small. It doesn't. There are not enough supply or resources to support them any carrying capacity. Okay, that's today's lesson. So here we go. The notes. How do I cut off my title? This is called logistic growth, and it's a companion to exponential growth, but a little more complicated. Higher level, typically a Cal 2 topic. So it goes like this. If I talked about, okay, does the bunny population really double every 2 years? Well, okay, it could double for a while, but it is limited by the resources. Food, etc. Carrying capacity, yeah? So, if you were to actually sketch the population as a function of time, then it would have to start at some non-zero amount. Yeah, you can't get bunnies from no bunnies. So you have to start at some non-zero amount, which would surely be the initial. And it actually does grow exponentially for a while. But what will it do as you approach the carrying cost?
Level out.
It'll level out. That's the shape of logistic growth. This is typically called L. L is the math variable for carrying capacity. Okay. What do you notice about the, give me some calculus on it. What do you notice about that? Okay, limit-wise, as x approaches, as t approaches infinity, p approaches L. What else? As t approaches infinity, p dt approaches 0. Okay. Derivative? Always positive. Secondary? There's an inflection point there. Okay. So all these things we'll talk about in a second. All right. Say we looked at this another way. A contaminated person infects another person every day. So the first day, well, one person would infect one other person. But on the second day, there would be 2 people infected. They would each infect another person. And now 4 people are infected. The next day, each of those 4 infects another person. And now 8 are infected. So that's exponential growth. It's multiplying, or it's exponential each time. But how is it limited? Let's think of it as a school.
There's a finite population.
Yeah, there's only a finite number of, I like population actually, let's go that. You can only infect so many people before everybody's got the disease, or at least everybody that can be infected will be infected, all right? Again, it's the same kind of shape. I don't think I have a single logistic decay graph in here. That was dumb. Because I think, all right. These are all examples of logistic here, all right? So say you're at lunch and Jenny tells a person a secret. And each of them, or her friend, each tells her best friend a secret. Her best friend told 2 other people, and those people told 2 other people. Is that exponential growth for a while? It is. And yet, why does it have a limit?
Because there's only so much people.
Yeah, again, so many people in the school, only so many people in the school to tell. So once everybody that cares to know it knows it, then you're going to limit. Okay? All right. I could do other examples, zombies, for example, but we'll talk about that in a minute. All right. Now then, oops, that's not the, now then, there's a part after this. Is there a part of this? Okay, here it is. All right. Now there are then, in exponential growth, there's one thing that affects how fast the population grows, and that's how many people there are, or how many bunnies there are, or how much money is in the account. That's all that affects it. In truth, however, in logistic, there's a little more. There's 2 things that affect how fast a disease spreads or a secret spreads. What is it? 2 things that would affect how fast it spreads.
The initial condition and like the rate that it spreads.
Okay. The initial condition will affect the amount, but it won't affect the rate. The rate. So that's, you're actually one step ahead. That will affect the amount. What affects the rate at which something spreads? Yes.
How fast it moves.
Okay, that's true. Yes. The constant of proportionality is rolled into the rate. What else? Okay, so in the deaf school there are 5 people infected. In this school there are 100 people infected. Where's the disease going to grow faster? What? Here, what? Because there are more people infecting to do the infecting. Do you agree? Are you with me? All right, so there's one thing is how many people infected. We'll just go with infected. Okay? Now, say I take that same case, let's tweak it a little here. Say over there are 100 people infected, and here there are 100 people infected. But over there are only 101 people in the school. And here there are 1,000 people in the school. Which one will grow faster? Infection. Yeah, and over there, it's going to grow at maybe 1 person more, right? But over here, it could grow by a lot more. So what else affects the rate at which the infection starts? Yeah, the infected and the uninfected. How many people are there left to infect? How many people infected and how many uninfected? And actually, I say 2 factors, but you're right. You guys said the rate at which something spreads and the disease, what do you call that? Biology people, spreadability is not a word. What the disease? Transmission, there's something, isn't there a word for it?
Transmission.
Infective, I don't know. I feel like you guys should know this. Transmission, okay. Disease, how quickly the disease transmits. Okay. I was going to say mortality rate, but that's like, it's not, that's a little gross, or grim. So let's look at it this way. In logistic, the rate at which the population changes, like population of bunnies or infected or rumor spreading, whatever, okay, depends on a constant of proportionality still, and how many people there are, but also how many people left to infect. How many people uninfected? Would you write under this, how many people left to infect? So, how many people left to infect? Now, first you would need to know how many people max. What do we call that? Carrying capacity. We call that L, okay? And so if we have a total of L and P represents infected, then how many uninfected? L minus P. There you go, L minus P. That is the differential equation for logistic growth. Okay, this is the infected. This is the uninfected. And this is the kind of problem-specific rate of transmission. You follow? Constant of proportionality. Okay, cool. Now that's actually the easy part. The hard part is not to get the easy part is the differential equation. The hard part is the population equation. Here we go. We have to develop the equation for population from that differential equation. So our goal is to start with dp dt is kp times L minus P. And at the end of the day, we're going to have a box for population is this. That's what we're trying to get. What is the population equation as a function of what will population depend? What's the independent variable? Time, yeah, as a function of time. Okay, so calculus time. What do we do? Separate the variables. So dp over P and L minus P equals k dt. Cool. And we're going to integrate. I'll integrate the right side, kt. Boom. You integrate the left side. Okay, so how do we integrate the left side? Partial fraction decomposition. We have to do partial fraction decomposition. So if we go 1 over P, L minus P, what are the 2 denominators we will use? Pn L minus P. Alrighty. Let's clear the fractions by multiplying by the common denominator. What do we get when we do that? 1 equals times the difference L minus P plus B P. Okay? Alright, how do we solve the equation? So many unknowns. Yeah, we let L equal. Okay? This is true for all L's, or all
No,
P's,
let
excuse
P
me.
equal L.
Yeah.
All P's. L is a constant. We can choose to let P be whatever, because this equation is true for all P's. So we can choose good P's that help us. What is a good P?
L and 0.
We could say let P equal L, and 0 will also help. So when P equals L, we get 1 equals 0 plus BL, so B is
1 over L.
1 over L. Cool. And if we let P equal 0, then we get 1 equals AL plus 0, so A is 1 over L. All right. You'll want to write small. We'll probably do at least 3 columns of work here. We're nowhere close. So here we go. Now our new problem is 1 over L over P plus 1 over L over L minus P dP on the left equals KT, KDT rather, on the right. Okay? Okay, integrate please. The left-hand side is 1 over L natural log of the absolute value of P. Now this is the one that we have to be careful on, because remember that is a function within a function, so at least mentally use of.
Negative 1.
It's negative. Negative 1 over L. Do you all understand why negative?
Yes.
It's L minus P, F, the dP, the du would be negative dP, there's a negative thing. So it's negative 1 over L, natural log of absolute value of L minus P. Wait.
Wow.
Okay, just like all these, we could put a C on either side, but it's best to put the C on the less complicated side, so we'll put the C on the right side. Follow? All right, now, write yourself a note, please. Wait to find C. I am going to, it's taking me years to nail this down to where it makes pretty decent sense. It helps to find C later in the game. So we're going to wait a second. Let's do some cleanup here first. What can you do to clean this up? Okay, I could combine my two, but they're different logs, so I can't combine them. What else? Log rows. I can't do log rows with the 1 over L there. Oh, you want to move 1 L over L up. You can do that, but that doesn't help. Don't do that. Okay, what else can you do to get rid of the 1 over L? Multiply it over. So let's call it natural log of P minus natural log of L minus P equals LKT plus LC. We multiply all terms by L. You follow? Okay. All right, now log rows. So how does that combine to the left side? Natural log of P over L minus P equals LKT plus LC. Right? A little more. What else can you do to eventually solve for P? Exponentiate. So absolute value of P over L minus P equals e to the LKT. Do you want to do it in separate? Can we break up already the e to the LKT, e to the LC? Are you cool with that? Okay. And it's multiplying. That's not adding. Make sure you've got that. You cool? All right. Now let's dump the absolute value. P over L minus P equals plus or minus. I'm going to write e to the LC first because it's constant, and e to the LKT second. And then again, this is just take my word for it. It makes our life easier. Let's take the reciprocal. All right. Now, if I take the reciprocal here, L minus P over P, it's just easier to work with. You'll see in a second. All right. Now, if you take the reciprocal here, then doesn't that mean e to the LC in the denominator, which is really like a e to the negative LC? You with me? And likewise, e to the negative LKT If I took reciprocals, they'd be in a denominator. If they're in the denominator, they'd be a negative exponent. That's where I'm coming from. Follow? Cool. Now, here's where we use the initial condition. Initial is at time equals 0, the population is the initial population, a lot like we do in exponential. Follow? Now, on the left-hand side, we would get L minus P initial over P initial. On the right-hand side, plus or minus e to the negative LC, e to the negative LKT. You cool? E to the 0. Sorry. Yes, thank you. So it'd be a big fat 1 there, yeah? Are you done? All right, now, it's typical then to say that is a ridiculous out front constant. I don't want to write that. It's a big freaking mess. I don't want to write that. It's a big freaking mess. And so we're going to just let A equal the whole thing. A represents L minus P naught over P naught, or plus or minus e to the negative LC. All that, I'm just going to write in A in its place. You down? Mm-hmm. All right. Now then, if I go back to where we left off when we went to put in the initial, then that means going back to where I leave off, I now have L minus P over P generally is, instead of plus or minus e to the LC, negative LC, I'm going to write a big fat A. And e to the negative LKT is, all right. So after I found the initial, I'm going back to the general equation, and I'm plugging in an A in place of that big mess of a coefficient. You with me? Okay. Now we still have the objective of solving for P. So how would you now solve for P? Multiply. I heard somebody say multiply P over. I like it. Okay? Now what? You go to solve for P. Move over to that P, yeah? So L equals P A e to the negative LKT plus P, yeah? So P is L over. Let's go, you typically write 1 first. It's just 1 plus AE to the negative LKT. Now, would you write underneath this, let's make sure we have all these nailed down, what they mean. P represents population, it varies. L is the carrying capacity. It is a constant. Problem-specific constant. You follow? Let's go to T. T is time, and it's the other variable. It also varies. Okay? K. It's a constant that has to do with the spreadability of the disease or how fast the population regenerates and all that stuff. Constant, problem specific. And last but not least, A. Now, A has meaning. A is L minus P initial to P initial. So A is a measure of something. What does L minus P not refer to?
How many is there?
From the originally not affected.
How many originally are uninfected? And the bottom is
From the affected.
infected. So it's the ratio of uninfected to infected. At time 0. Okay? So A is a measure of how much growth room is there. Is there room for a lot of growth? Or are we starting off with so many infected that there's only a few left to it, kind of thing. You follow? Okay. Now, given the shape of the graph, why does this equation make sense? So would you give me a quick sketch of the graph like this, yeah? And then let's talk about the equation. Oops, population, I was using P not A, sorry. Population, population equals L over 1 plus AE to the negative LKT. This is one of the reasons I think math is so cool. Oh, it makes sense. All right, so check it out. As time goes to zero, or sorry, as time goes to infinity in this equation, what does e to the negative LKT go to? Negative infinity, yeah? Goes to e to the negative infinity. Yeah? And so what is L over 1 plus AE to the negative infinity go to? What does e to the negative infinity go to? 0. And therefore, this approaches L over 1 plus 0, or, well, so it makes sense that that equation would generate a behavior that approaches L as time goes on, yeah? What about, is there another thing in there I wanted? What about at would that be of any interest at time 0? I don't actually know. Is that interesting to us? And so P initial is 1 plus A. I don't know if that's not really interesting, is it? Sorry. 1 plus R minus P initial over. Is that true? Even what the freak? Yeah. Oh yeah. So if I multiply through by P initial, that's not going on. Never mind. Forget it. Okay. What's that? How did I get e to the negative infinity? Okay, so as time goes to infinity, because of the negative, so basically I'm looking at what's going on here. Would you agree that as time goes to infinity on the graph, the population should be starting to approach the carrying capacity, according to our graph model, yeah? So what I'm trying to show is that that equation would bear that out. So if I think about as time gets really big, remember this is like e to a negative is like over e to the LKT. So wouldn't you agree that as time gets really big, this e gets really big, and therefore this approaches 1 over big, so it goes to small, yeah? And if that goes to 0, then a times 0 goes to 0, and population starts to just approach L over 1 only, and so population approaches L. The equation generates that behavior that we expect to be graphical. Okay. Consider the zombie question. At what point is the population growing the fastest? So think about, so say there are 1,000 people in the school. When will the population be growing the fastest?
When the amount affected is the same as the amount unaffected.
Why? That's true.
Because it's 1 to 1.
Yeah, it's a 1-to-1 relationship. Every zombie's got somebody to infect, yeah? At the first, when there's only one zombie, yeah, there are 999 people left to infect, but there's only one zombie doing the infecting, yeah? So it's when there's a perfect match. So think of it this way, when the population is exactly half of the carrying capacity, then that's a 1-to-1 relationship between infected and uninfected. All right? So in logistic growth, the population grows fastest when the population equals 1/2 of L. Let's prove it. Seems logical on the surface, but let's prove it. So how would we prove a maximum growth rate? Second derivative, yeah, it's the maximum growth rate is the max of dp dt, yeah? So if I take the derivative of the population, now keep in mind, here's my equation, yeah? Okay, so if I take the derivative of that by product rule, first stays the same, derivative of the second is? What's the derivative of L with respect to time? 0. What's the derivative of P with respect to time? Negative dp dt, yeah? Plus second stays the same. L minus P times what's the derivative of the first? K d dp dt, yeah? If we pull out a K and a dp dt, what's left in the first guy? Negative P. And in the second guy? L minus P. So we get something like K dp dt, negative P, negative, so L minus 2P, yeah? Yeah? All right, so if I want to find max of these, actually, isn't dp dt kp L minus P, yeah? Okay, so where would the zeros be? When P equals 0, can that happen? Remember, that's not time, that's population. Can population be 0?
No.
Yeah, you can't grow exponentially if you start with nothing, so that's not possible. What about L minus P equals 0? When P equals L, graphically, we, however, know that that's not a max growth rate, that's a min growth rate. That's the slowest growth rate. It's always positive, but you're approaching the slowest possible growth rate. That's min growth rate. And the last possibility then is if L minus P equals 0, which means when the population is 1/2 the carrying capacity. So that inflection point is where the growth rate is the fastest, or the growth rate is the greatest. And it is where the population is exactly halfway to the carrying capacity. Follow? So this would be that one. You cool? Okay. Alrighty then. Now you'll be happy to know that you don't always have to do all that integration because it's a mess. You really need to know how, kind of like an exponential, you need to know how to plug in the cases they give you to find the K, and then once you know the K, you can solve questions. You with me? You need to be able to do that here. So let's go with a problem that you might see. The population of a species satisfies the logistic differential equation. dp dt is P times 2 minus P over 5,000, where the initial population is given and T is in years. What is the limit as time goes to infinity? Now, would you write over here, this is a form some textbooks use. Ours, it's kind of an even split. Some books use a slightly different form of logistic, the equation of the differential equation. You need to be able to work from one to the other because I don't know what you want to call it. You might be using one book and another might be using another. It's not a big deal though, don't worry. It goes like this. If we answered this question, the question is, all right, as time goes to infinity, what does population approach? We know from the big idea that as time goes to infinity, population should approach L. So really the question is, what is L? Right? Carrying capacity. Now, what I'm talking about here is this form is not quite like ours. Ours looks like this. And this is what your eye should draw. Okay? Our form uses a straight up P, nothing else, no coefficient. So to get it to be like our form, we need to dump the 5,000 or somehow algebraically tweak this so that 5,000 is not there. What could we do? Factor out a 5,000. Okay, dp dt is, if I take a 5,000 out, then surely I can take it out of the second term, and that's great, it makes p, but I also have to take it out of the first term. So what does that 2 then become? Does it become 2 over 5,000 or 10,000? 10,000, because that's what would work if you multiply it back together. Do you agree? Now, it's easy to see what L is. What's L? L is 10,000. So it seems like based on that differential equation, it must be the case that population carrying capacity in this problem is 10,000. You with me so far? Okay. Now that's one way to do it, to make their form look like our form, so I could say, oh, there's L. Another form is by just kind of using your noggin, understanding the graph for logistic growth. We know that as time goes to infinity, yes, population approaches L, and that's true, but think growth rate. dp dt approaches 0, okay? So look at that equation that they gave us. And ask yourself, what p would make this 0? Now, obviously, 0 would work, but we know p can't be 0, so think inside. What p would make that 0? 10,000. If p was 10,000, then the growth rate would be 0, and that's what would indicate dp dt is 0, which is what happens at time goes to infinity, right? So another way is to say, what would make the growth rate 0? Now, without integrating, we're not going to take this differential equation, separate the variables, and do all that. We're not going to do that, okay? Instead, we're going to write the equation for population just based on knowing what goes where. So remember, the equation goes like this. And to actually complete the equation, we need 3 things. We need to identify what's L, we need to know what's K, and we need to know A. So, what is L? 10,000. We found that already, okay? Remember, back up here, we said dp dt was 1/5,000 p times 10,000 minus p, yeah? Now when it's in that form, what else do you know? Hey, yeah, this is K. So K is 1 over 5,000. Now A, remember where A comes from. It's the uninfected, L minus P naught, to infected, P naught. What's L? 10,000. What was P naught? They gave it to you somewhere.
30,000, no, 3,000.
3,000 over 3,000. So as far as the uninfected to infected rate, or the room for growth kind of rate, you might think 7/3. Now with that, we have the equation. Population is 10,000 over 1 plus 7/3 e to the negative LK. What's LK? Actually, for the purpose of notes, we'll just not simplify, right? And then negative 10,000 times 1/5,000 t, but obviously we call that negative 2t. You follow? Okay. Does that make sense? All right. A zombie epidemic infests the school. When one zombie comes to school on Monday.
Yes.
The epidemic follows the logistic growth model so that the rate of growth is proportional to 3. That's one of the big ideas. The differential equation for logistic is the rate of change relates to
The amount of people.
number of zombies and number of people, or non-zombies, whatever. I guess we'll just call it people, yeah? Or infected and non-infected. Or bunnies and room for growth in the population for bunnies. Right? Okay, so would you interpret the proportional statement as a differential equation? And write the equation for population of zombies over time. So what is the differential equation for logistic growth? dPdt equals Kp times O minus P, and I don't think the school, so maybe we can do more. What can we put in right away? L, we can do L. But I don't know K. Right, you with me on where that thousands come from? Okay, cool. I don't see what else I can do there, so I guess I'll proceed on. Use your equation to find how many zombies, oh, that's a differential equation. Now I'm going to write the equation for population of zombies over time. So I need the population equation. Gosh. So I know L, 1 plus AE to the negative AT. What is, so we know L. What's L? 1,000. Okay. Let's go over to the side and find A. A is uninfected or non-zombies at the start to zombies at the start. So yeah, what's the zombies? 1 to non-zombies. 999. Okay, so A is 999 at time 0. E to the negative 1,000, and I don't know K. So in that sense, it's kind of like those exponential problems. We don't always know K. Just for the initial amount, you don't get K. To get K, don't you need another case? Okay, this is the same. So with another case, you can find K. What's another case? After 1 day, there are 25 more people. More, underline more. Okay? Because that implies that the population is 26 when the time is 1. Negative 1,000 K. And when you put in time of 1, that leaves you with only K unknown. Okay? Okay. So we're going to solve for K here, yeah? You'll gradually get really good at these and you won't show all this work, but first time through, I'll go relatively slow. Wouldn't you agree I could clear the fractions? Or cross multiply. So I could divide by 26, subtract 1. So divide by 26, subtract 1, divide by 999.
Take the log of that.
Take the log of that.
And then divide that by negative 1,000.
Divide that by negative 1,000. Don't you feel like so proud of yourself that you're so smart sometimes? You did all that freaking math just to...
I still understand what it is.
So I think you should appreciate how smart you are once in a while. Not everybody can do what you do. So, do you agree with that, K? Are you with me? That's pretty common in work. That if you've identified here, this is what K is, you definitely don't rewrite it like that. You just call it K from now on. And when people want to know, hey, what's K, they can look back and say, oh yeah, there's that freaking math. You with me? All right, so we know K and we know our equation. Our equation is complete. That's the population equation for any time. Okay? All right, so if I wanted to use my equation to find out how many zombies on Thursday, then how many days is that? From Monday to Thursday is? Just checking. Okay.
Monday doesn't get included?
It's a time, we're not counting the inputs. So if you do it from Monday to Tuesday is one day. From Tuesday to Wednesday is one day. From Wednesday to Thursday is. So no, we don't count zero. In other words, when you count to 3, you don't count 0 as a number. Okay, so it's 3 days. All right. So if you were to throw that in, I assume you would get more than 25, because that's how much is after day 1. Yeah.
Yeah.
We should put this. Should we take the time to put this in our calculator?
No.
No, I don't want to. Okay, so let's assume that's a number more than 25, which you better meet, or else we messed up. Okay? How would you use your equation to find the time when there would be 600 something?
Population 600.
Population is 600, and you would go something like this. You would probably store K, because you don't want to type in that big mess, and you're solving for T, okay? Okay, so tell me, what would you do to solve for T?
Cross multiply.
Cross multiply, and when that was over there, what would you do? Imagine this is over there.
Divide by
You
600.
divide by 600,
Subtract 1.
you subtract 1,
Divide by 999.
divide by 999,
Take the log.
take the log of that,
Divide by negative 1,000.
divide by negative
1,000K.
1000K. And there's your time, and what would the units be?
Seconds.
Days, 6 days. Okay?
That.
Days since Monday, really. You follow? Okay, for the first Monday, whatever. All right, that is that, logistic. I can't believe I got through it all. It's really hard to get through this up here. All right, here we go. We might have to finish questions tomorrow, but 8, okay, 8 was a bit of a humdinger. I'll put the key online. So 8, the trick. I can get you started. I thought, why am I so mean? Why would I do this? Putting an odd number here, that's the worst, okay? But it is what it is. Get over it. Life is ugly.
There's an X cubed. It's 2x cubed.
2x cubed?
Yeah. 2x cubed.
Oh, like that?
Yeah.
So I actually made this worse for you?
Yeah.
Wow. I must have a lot of respect for your smarts, baby. Trig semblance of mass. Okay, so here we go. So, was the division the issue? Do you need to check the division?
Yes.
I got 2x plus 10 plus 38x minus 60 over x squared minus 5x plus 6. Is that what you got when you divide? Okay, cool. Shall we go back and show where that comes from, or just move on to the trig sum? Okay, so trig sum, here we go.
Cole can't do it, no.
I think you'll agree that the 2x plus 10 is a non-issue. We're just going to focus on the 38x minus 60. So in other words, you're going to break this into 2 integrals. You don't want to trig sum the whole thing, because obviously you don't want to put a freaking secant or tangent into that thing, right?
Well, that's what I did.
Why would you? No, no. You would definitely not do that. So you only want to trig sum the second part.
I don't know.
What are you thinking? So can we agree that this problem is not hard? You made it hard.
No, I know. It was still hard.
It's still hard.
I don't
Okay.
know. What I have looks easier than what Cole has.
All right. So this is x squared minus 5x. Ah, shoot. I'll post my key online. Keep it till tomorrow. We'll go over it.
Oh, yeah.
Have a good day.
Do you also set the notes for tomorrow?
Yes. Oh, yeah, yeah, I have this is a little, it says that this is set for 6 months or 6 weeks using the course. That's what the plan is. The back is teaching a little ahead of time some stuff that we get to. So we should probably watch this.
By zoning out. I can't stay at 100%.